Right, so it's a pleasure today to introduce our speaker, Ben Bloem-Reddy. So Ben received his PhD in statistics from Columbia in 2017, and then he joined UBC Statistics in 2019 after doing a postdoc in Oxford. So we are very fortunate to have him at UBC. So he's doing highly original work in probabilistic and Bayesian approaches, both theoretic and methodological, including methods based on symmetry, network models, as well as inference using SMC and MCMC. So I'm really excited to hear today about his the latest of his work on invariant neural networks, which is already having a profound impact in machine learning. So I will now yield the floor to him, and thank you all.
Thanks, Alex, for that really kind introduction. And thanks, everyone, for coming to listen to me speak today on what is such a nice sunny day. This photo on my background was taken a while ago, but probably doesn't look too different from that today. It's only 5 minutes from where I am here on campus. So anyway, thanks for being inside, at least for about an hour. If anyone has any questions as I go along here, raise your hand, or as Aaron said in the chat window here, type your question in the chat window, and I will try to answer as we go. Otherwise, if I've timed things correctly, we should have some time at the end for questions. So, right, so before diving into it, I'd like to acknowledge that UBC Vancouver is located on the traditional, ancestral, and unceded territory of the Musqueam people, and fortunate to be here for our work and living here. So, okay, so I'm going to talk about invariance in statistics and machine learning with a focus on machine learning. And invariance just happens to be a really nice way to think about the following setup. And this is really something that most of us are engaged in one way or another. And the idea is we have some data, say it's a medical image. Here it's a CT scan of some lungs. And we'd like to infer something from that data, whether it's the probability that some nodule is malignant or benign, or something about a process that gave rise to this. So at a high level, we have some data and we want to infer things about it. And depending on the task, there might be things that we don't want our inferences to be influenced by. Okay, so I have some examples down here in the bottom. Things we might not want to be sensitive to are the orientation of the image. So if we apply a rotation to this image, well, whether or not this nodule highlighted in blue is malignant or benign shouldn't be sensitive to how we actually feed our data into our, say, our neural network or any other data analysis procedure. And sort of maybe a more classical example with a more modern twist is if you have two different clinics that are doing the same thing, and say there's some imaging artifact in each of these clinics that happens to be correlated with this thing that we're interested in, we also would like to not be sensitive to that. Okay, so this is a much harder thing to formulate. So I'm just going to say this is something we hope to be able to actually get to, but for right now, the most we can say is in terms of these types of well-defined transformations of our input data. Okay, so that's what I'll focus on, and I'll start by describing an even sort of simpler version of this. That's nicely described by a quote that is attributed to Goethe, which is, "The tissue of the world is built from necessities and randomness." Okay, I actually can't find the original citation to this. It's from a textbook about randomized algorithms, but if anyone has the original citation, I'd be interested to have it. So let me know if you've come across this before outside of this textbook. And the idea here is that the necessities are the things that we really want to learn about or use for our inferences, and the randomness is everything else that we would rather ignore. Okay, so my research and what I'll talk about today is really trying to develop a mathematical and statistical framework for how we can achieve this separation in different types of problems, and then also quantifying the benefit of doing so. Okay, so my talk is going to focus on a mathematically nice and somewhat prevalent version of this, and a really simple cartoon of that might be, okay, we have an image, and it's too bad we can't do this live because I would just cold call someone in the audience and ask them what's in the image, but I think everyone would say there's a cat in that image. Okay, if I rotate that image in two different ways, there's still a cat in that image. If I zoom in and crop it, there's still a cat in that image. If I change to black and white, there's still a cat in that image, right? So there's something invariant here, and that, you know, as humans, we process this as the concept of a cat being in the image, and ideally we'd like to incorporate the same type of invariance in our statistical and machine learning procedures. Okay, so to actually formalize this mathematically, this is going to be I think my notationally heaviest slide, but the basic idea here is we'll be thinking about input and output spaces. So X might be the space of images, Y might be a space of labels of animals in those images. And the thing that really will drive what we're talking about when we mean invariance is a set of transformations, script T here. Okay, so in my previous example, it might be different 2D rotations of the image. It might be scaling and cropping. It might be turning it into a grayscale image. But as sort of a mathematically abstract object, this is a set of transformations. The thing that we typically require for the nicest type of theory is that the set of transformations is a group. Okay, so a group has some certain algebraic properties that I'm not going to get into too much in this talk. But the idea is that we have a set of transformations that will act on our image, and that action is actually expressed by this function phi. Okay, so this function gets an element of the set of transformations. It gets an element of my input space, and then it returns a transform version of that input space. Okay, so in the cartoon version from the previous slide, we might have that these transformations are 2D rotations, and we apply a 2D rotation to an image, and we get another image. Okay, it's just rotated. Okay, so those are sort of the main players for actually expressing what we mean by how we're going to transform our data. And then the key versions, or the key expressions of invariance or symmetry are as shown here. So if we have a function defined on our input space, then an invariant function returns the same value even if we apply some transformation to our data. Okay, and this should be true for all transformations in our set of transformations. Okay, so this is invariance, and then there's an equally important notion of equivariance, and the idea here is that the action of the set of transformations commutes with the function. Okay, so this function f is equivariant if I can apply a transformation to my input data, and that's the same as not applying the transformation to the input, just running the input through the function f and then applying the transformation to the output. Okay, so how this set of transformation acts on the input and output space might be different, but this is the basic idea. Okay, so these are the two notions of symmetry, and I'll just use the word symmetry here when I can. If I need to distinguish between the two, then I will actually say so. Okay, so these are the main players in actually setting this up mathematically. And the key idea here is that this action of the set of transformations on the input space, when it's a group, induces equivalence classes on the input space. Okay, so here, if we're thinking about rotations, then any point on this orange circle is equivalent under the action of this set of transformations. Okay, any point on the blue circle and green circle. Okay, so the basic structure here is that our action induces equivalence classes in our input space, and this is really what drives everything. Okay, so are there any questions on just sort of setting that up? Okay. Great. So this is the basic setup, and it turns out can be quite useful. Okay, so I'm going to spend the remainder of the talk telling you what and how we can actually do this in practice. So what can invariance or equivariance look like with probabilistic models, or, for example, neural networks? Okay, and this is sort of, we can make the most general statements when T is a group, when the set of transformations is a group. We can generalize these in a few different directions to non-groups, but things that are nicest when we're dealing with a group. And so this is what I'll be talking about primarily. Okay, so we can actually characterize what our models can look like when we want to enforce invariance or equivariance. Okay, and this begs the question of why we might want to do that, why we might jump through hoops to understand how we can do it. I think probably most of us here understand that in practice, at least in deep learning, this is sort of standard practice now. So I probably don't need to appeal to you too much based on experimental evidence. And so I'll try to describe some efforts to describe this theoretically, which is ongoing work and has some open questions. Okay, and then at the end, I'll briefly describe some of my thoughts about how we might extend these ideas and what might be next. So. Okay, so to start, we're gonna focus on what the structure of invariant models can look like. Okay, and I'm a statistician. I have a background in Bayesian statistics, so I speak primarily in terms of probability distributions. We can say basically equivalent things in terms of functions, and I'll do that in a minute. But the idea here is that if we want invariance in our models, and here we're trying to predict, say, the label of the animal and image. So we're predicting some y from some x. Okay, so say input image and the label of the animal and the image. When we suppose there's some invariance, we assume there's some invariance in our model, then really what we're trying to do is learn a conditional distribution of y given x, so that the conditional distribution of y is the same no matter how we transform x. Okay, so I've dropped the subscript on the action there just for convenience, but the idea here is that we want this notion of conditional distribution being invariant when we act on x. Okay, so should have more pictures here. Okay, so I showed you this on a couple slides ago, and these equivalence classes are called orbits. Okay, and this comes from the group theory literature. But if we look at these equivalence classes of x's, this is any value in input space that I can get by applying a transformation in my set of transformations. Okay, in my set T. Okay, and the idea is that we want the conditional distribution of y to be the same no matter where I am on this orbit. That's exactly what this restriction says. And once we see that, then the structure of these conditional distributions is actually quite easy to describe. All we need to do is know which orbit we're on, and then we can simplify our model using what's called a maximal invariant. Okay, so the basic idea here is that if we can compute a statistic of our input that tells us what orbit, what equivalence class we're on, then all of the hard stuff, all of the hard learning part is learning the conditional distribution of y given our maximal invariant. Okay. So this has, I'll just say as an aside, this has connections to ideas from classical statistics of sufficient statistics and things like that. I'm not going to go into it in detail here, but the basic idea here is that we get this big simplification of our problem just by requiring this invariance. Okay, and so we can formulate this in terms of functions. Okay, so these are equivalent, but it's easiest to describe in the case of a compact group. Our conditional distribution of P of y given x has this invariance property if and only if y can be expressed as a function of this maximal invariant and some random noise. Okay, so we can always, we know that for any y that's jointly distributed with x, if it's invariant, if its conditional distribution is invariant to the set of transformations T, then that sort of separates the problem into two parts. One is learning, coming up with a maximal invariant M, and the second part is coming up with the relationship of y to the maximal invariant. Okay. So I see Madi has their hand raised. This is probably a good time to take a question.
Oh, sorry, but just to understand, what for rotation, for example, the theorem says that there exists a function that only the distance from the origin matters plus a noise, right? Because you have done the dimensionality reduction to like radial functions, right? Yeah. Is that what the theorem says?
Yes, that's right.
Okay, yeah,
that's right. Thanks. Yeah. So for known groups, for a lot of groups, we actually can write down what a maximal invariant would be. In practice, you know, if we're dealing with images, writing down a maximal invariant is not so straightforward. And it seems that what we're doing with neural networks is actually trying to learn something like a maximal invariant. Okay, so I'll come back to that a bit later in the talk. Okay, but the basic idea here is that when we have this invariance with respect to a set of transformations, that induces this equivalence class structure in our input space that is greatly simplified by just identifying the equivalence classes. Okay, so this is an if and only if statement. So we know that this always has to be the case. I will say the maximal invariant is not unique. So we can take one maximal invariant and map it, put it through a one-to-one mapping, and we have another maximal invariant. So this is somewhat silent on various statistical issues, but this is sort of a first step in characterizing what we can and should be doing with these models. Okay. Okay, so we have an equivalent, or not an equivalent, an analogous result for equivariance, and the situation is a little more involved here. So the basic idea is conveyed by the name. So y and x equivary or covary with the action of t, of our set of transformations. And so you can show that this is really the right criterion where our conditional distribution of y given x shifts predictably. If we transform x, then we need to correspondingly transform y. Okay, and this really is easier to process in terms of joint invariance. Okay, so if x is also marginally invariant in distribution, then this amounts to a joint invariance. But even just in terms of the conditional distribution, the idea here is that if we transform x, then our conditional distribution of y needs to transform accordingly. Okay, so when we do that, then the structure still relies on these equivalence classes, but now we need to put orbits of x in correspondence with orbits of y. Okay, so we need to know that if we move a point along its orbit somewhere, and then we look at the distribution of y needs to have a corresponding movement along its orbit. Okay, so we can actually formalize this by setting up a coordinate system of orbit representatives, and so that these are the stars on these equivalence classes. And so the idea is that I need a function that will map any point on this orbit to the star, and any point on the blue orbit to the blue star, and any point on the green orbit to the green star. Okay, so these are actually maximal invariants. They just represent the orbit. Okay, and then once I have those, then I can take a transition into y onto the set of orbit representatives in y, and then just undo the transformation that I had originally applied to x. Okay, so in math, you can show that our distribution P, conditional distribution, has this equivariance property if and only if it can be obtained as follows. So this is, we need to unpack this. There's a couple of function compositions here, but this function tau is exactly what I said before. So it maps x to its orbit representative. Okay, and then I pass it through some function b. It doesn't matter what. Some function b that takes us into y space, and again we can have a random noise variable here. Okay, and then once I get into y space, I need to undo the transformation that I had applied to x originally. Okay, so this guarantees exactly this equivariance property, and again it tells us exactly how and what we might do if we want equivariance in our models. Okay, so this idea of equivariance is not so common in statistics, and there's some work in the classical statistics literature on equivariant estimators, but in general, invariance is a much more common thing. So there aren't a lot of sort of nice analogs to describe in the statistics world. But equivariance has been showing up all over the place in deep learning. So I think it's easiest to just sort of describe why we use equivariant functions at all, or models at all. And this is with deep learning. So the idea is that with any neural network, it's composing simple functions over and over and over, and that's the deep part. Okay, so the idea here is that if we want an overall invariant function, we compose a bunch of simple equivariant functions and then make it invariant at the end. Okay, so there's some nice work within the last couple of years that shows that equivariant linear maps are, this is an if and only if convolution. Okay, so equivariant, a linear map is equivariant if and only if it can be expressed as a convolution. And this sort of goes in with our intuition, because convolutional neural networks have been the backbone of deep learning, especially with images for a while now. And so there's been a whole bunch of work in the last few years extending these ideas to other groups and other data types. Okay, but the basic idea is the same. I have my input x, I pass it through some convolutional layers. Okay, these are simple equivariant functions. I perform some invariant pooling, and then maybe I put a fully connected network at the end, and that whole thing actually works really well in practice. Okay. And did I see, was there a hand up a minute ago?
Yeah, just I was wondering if you could go back one slide.
Yeah.
Here in the middle, there's this forms of functions that you didn't talk about. Is this could you say something about what these are
Yeah.
on the vertical line?
Yeah, that's a good question. So this is, the idea here is that this is sort of a cartoon of my set of orbit representatives. Okay, that's the vertical line. And the idea is that each orbit representative induces a distribution on the orbit representatives of y. Okay, so these are, say, probability densities on orbit representatives of y. That depending on which orbit I'm on in X space, then I might have a different distribution over y. Okay, so that would be sort of part of the inference or the learning task, and the equivariance is taken care of entirely by this sort of coordinate system that maps points on orbits to their representatives in both X and Y, and then undoes that map in Y space. Okay.
Thank you.
Yeah, it's a good question. Okay. Right. So in deep learning, of course, most things are done with deterministic functions, and so we can discard this random noise. We can think of it either as averaging or just discarding it. Doesn't change any of the results, and the basic structure has to be the same. Okay. Okay, and again, I should point out this is sort of a general representation result, and it remains silent on statistical issues, which are important. And this is ongoing work, is to try to really understand, how we actually might learn good functions here. Okay. So in deep learning, we sort of know that these get used all the time, and as I mentioned, there's been a whole lot of research in the last couple of years working out the details of how to implement convolutional layers for different symmetry groups, for different data types. It's actually a pretty big literature now, and I don't even feel comfortable saying that I know all of it. So it's been interesting to see. There's been a lot of work in that direction, and that begs the question, why? Right? And I think at some level we might have a somewhat intuitive understanding of this. And the high-level argument is as follows. So if we think of requiring our models, whether it's a neural network, which we're just thinking of as this big flexible function, whether it's a neural network or a probability distribution, requiring invariance or equivariance or some sort of symmetry imposes constraints on that function or that distribution. Okay, so the more symmetries, the more constraints, and the more constraints, the fewer functions or distributions there are that actually satisfy those constraints. Okay, and so when we're specifying a model, if we're saying, from a sort of a classical statistical modeling standpoint, we have a family of distributions, and we want to infer which one might be the best fit to our data. Imposing these symmetry constraints actually limits the size of our models. Right? There are lots of distributions that don't satisfy those constraints, so we can't actually use them in our model. And likewise, if we're using a neural network, and thinking about the sort of class of functions that we might be representing with that neural network, fewer functions actually satisfy these symmetry constraints. Okay, so the size of our models is limited, and it also turns out that in some sense, what's left, the functions or distributions that actually do satisfy all the constraints imposed by symmetry, are relatively simple. Okay, we can make this precise in certain examples, but at a high level, the functions or distributions that satisfy these symmetry constraints are simple. Okay, so the punchline here is that imposing the right symmetries throws away unnecessary complexity. Okay, and so we'd like to make that mathematically precise. We can do that in some simple cases, and work here is ongoing. And so I'll get to that in a minute. But I will say that, you know, as someone who's working on theory and methods, and in this case, you know, more on theory, trying to understand something that seems to work well in practice in a lot of situations is one of those nice problems, because you know there's in some sense a right answer, and you just have to find it. So this stuff we know works really well in practice, so well that it's standard, especially when you think of image data. What's your default neural network architecture? Well, there's a convolutional architecture in there somewhere as the workhorse, right? So it's become so standard that we don't even really think about it. And so one way I like to think about this, and statisticians in the audience might recognize something like this from George Box. So as a general rule, convolve what you can and augment what you cannot. Okay, so George Box said, block what you can, randomize what you cannot in terms of experiments for causal inference. But in this case, if we know there's symmetry or invariance in our problem, or assuming that there is, a general rule is convolve what you can. So use a convolutional architecture when you can, and if you can't, then augment. Okay, and data augmentation is as follows. So let's say we haven't worked out a convolutional architecture, or it's a real pain to implement, or we just haven't engaged, we haven't been able to keep up with the literature on this stuff, but we have a set of transformations that we would like to be invariant to. Then this is a really general purpose tool, where during training of our neural network, or statistical model generally, for every example, we apply some random transformations to it, and say with the neural network, maintain the same image. Okay, so we're basically showing the neural network examples of transformed inputs that correspond to the same output. Okay, and this is exactly the type of structure that we would like to be able to represent, and we're just doing this during training. Okay, so that's data augmentation. And as I said, it's quite general. So in this case, our theory with convolution really stops at groups. There's been a few extensions to, say, scale invariance, but most of our theory stops at groups. But data augmentation is super flexible. You can do it with anything. Okay, you don't need a group. It's just transformations of your data. Okay, and the benefits of this manifest in a few different ways. And I like this as a case study for highlighting exactly what this sort of simplified structure of invariance buys us. So if we think about the empirical risk and doing, say, empirical risk minimization with data augmentation, we can write our empirical risk of say, a classifier f as follows. So we have our loss function, which typically is a function of, or looks at our predictor f, or a classifier f, evaluated on some input data, and compares it to, say, the label. Okay, data augmentation, if we were to do this exactly, averages with respect to some distribution of transformations. Okay, so we apply some random transformations to our inputs, and we get this sort of augmented risk. Okay, well, in the case of a group, and actually I think we can say something a bit more general here, but in the case of a group, this corresponds to averaging over the orbits of X. Okay, so if you have equivalence classes induced by your transformation, the action of your transformation, then data augmentation is actually averaging your loss over these equivalence classes of the inputs. Okay, and so there's a couple of papers, one in NeurIPS and then a much longer extension in JMLR by some researchers at University of Pennsylvania that look at this in quite a bit of detail, and there's some nice theory showing that training with data augmentation or a data augmented predictor actually reduces the variance and leads to improved, say, mean square error and statistical efficiency and all sorts of things. Okay, so that's nice. I mean, the structure here is just that you're taking a conditional expectation with respect to the orbits. Okay, so this is the same as saying, well, I know my input lies on this equivalence class, this orbit, and so I can just average my loss over that orbit. Okay. So there's a related technique called feature averaging, and it's almost trivially it's, I guess, so related that it's almost not different. But the idea here is instead of averaging your loss, you average your neural network, and then check your prediction based on the average neural network. Okay, so of course we don't make different copies, but this just is a cartoon where, again, we apply different transformations to our image, to our input data, and then we average our neural network, and then we get sort of this averaged prediction. Okay, and I think in practice, typically this averaging is done somewhere internally in the neural network. That's why it's feature averaging. Okay, but the idea here is that we're averaging the output of the neural network before we evaluate our loss. And this gives us something almost for free. So if we have a convex loss where I need convexity in the first argument, then with Jensen's inequality, when I move, so if I start with my augmented risk from data augmentation, if I move my expectation inside the loss, then I get potentially a boost for free, almost for free. Okay, just a bit of changing where I take the average. Okay, so that's nice in practice. Actually, we have some experiments that show even if you train with data augmentation, that if you apply feature averaging at test time, you typically get a boost, which is nice. But it also lets us do a bit more theoretically. So we can see where symmetry is advantageous through looking at feature averaging and looking at a certain type of generalization bound. So generalization bounds, for those of you who might not know much about these are typical tools for sort of quantifying how well we can expect say a classifier to do, or a trained neural network to do. And there are two main categories. There's uniform generalization bounds and PAC-Bayes, and there's been a lot of recent work sort of going between the two. So the PAC-Bayes bounds are, at least in this case, easier to interpret. So I'm gonna talk only about those. But the idea here is that we can start with a randomized classifier, and this can depend on the data. So you can think about this as, say, in practice, what it's done is we train a neural network and then we add some noise to the weights, okay, and that induces this distribution over say classifiers, okay, and then we need a reference distribution, which is known in the literature as a prior. This is not to be confused with Bayesian inference, which actually updates from prior to posterior, but really this is a reference distribution, okay, and it can't depend on the data. Okay, at least we'll keep it simple here and say that it can't depend on the data. And so the idea here, the general form of a PAC-Bayes bound is that with high probability, that if we learn some randomized classifier that depends on the data, we can bound the true risk of that randomized classifier by the empirical risk and this term that involves the KL divergence between Q and our reference distribution. Okay, so the name of the game a lot of times is actually finding a reference distribution that gives us a small KL term, and especially with neural networks, our empirical risk often is close to zero or exactly zero. Okay, so in practice, this KL term will dominate. It's also the problematic one for actually computing in practice, and I'll say more about this in a second. Okay, but this is the general form of a PAC-Bayes bound, and when we have feature averaging, this is really useful for actually understanding what's going on. So, so we think about what we're doing is feature averaging when we average, say, our neural network with respect to transformations. If we write this as an integral, then we can think of this just as an operator on functions. Okay, so this bold S is just an operator on functions, which produces another function which is invariant to this set of transformations T. Okay, so if we have some class of functions and we think about symmetrizing every function in the class with the symmetrization operator, then if we have two distributions on that class of functions, then their image measure is, oh, this inequality is the wrong way. This should be greater than or equal to. So pretend that's going the other way. Their image measures are closer together. Okay, and the idea here is that, and we call this the symmetrization gap, this difference between these two KLs. And the idea here is that by symmetrizing, we are taking our original function space and it will induce equivalence classes of functions through this invariance. And basically it's compressing that function space. Okay, and so any distributions that we define on the original function space also get compressed. And so the KL gets smaller. Okay, and that actually shows up then in the PAC-Bayes bound. Okay, and this is a really simple argument. This is just follows from the data processing inequality and isn't necessarily special to the symmetrization. I mean, any compressive map will get you this, but the idea is that when the symmetrization reflects actual symmetries in your problem, you don't pay a price in the empirical risk. So you can do just as well with your empirical risk, and also get a gain in this KL term. Okay, so that's a nice simple picture. In practice, there are some important caveats here. So when we're computing this KL term in practice, say with neural networks, it's usually indirect. So we think about defining these distributions on function spaces. In practice, they're usually in terms of neural network weights, and that mapping is not well behaved and not something we can work with in closed form. And in particular, we don't know how to compute the symmetrization gap. So we have a nice mathematical expression for it, but in practice, we don't know how to compute that, and so we don't actually know how beneficial the symmetrization can be. That's something we're working on to try to handle. And then another thing that I find really interesting is the theory, both with data augmentation and with feature averaging, is in terms of learned trained functions, trained, say, neural networks. But as always, training, especially with stochastic gradient descent, muddies the theory quite a bit. So when we run our experiments, if we train, say, with exact data augmentation, or exact feature averaging, or even a large number of samples from this group of transformations, a set of transformations, it actually seems to hurt generalization. So when we train with lots of augmentations, or lots of terms in our average with our set of transformations, then what we learn actually doesn't generalize well. And we're trying to understand this, but our best guess is that the variance reduction we get from augmentation of feature averaging actually hurts us in training, right? So there's a lot of theory there's a lot of work that indicates that the variance of the gradients is a pretty good predictor of how well a network will generalize, and if we sort of wipe out too much of that variance, we kind of kill ourselves with what we learned. Okay. So those are just some caveats and what I think are some interesting problems. Nonetheless, our advice, I'm adding to what I said before. So convolve what you can, augment what you cannot, and feature average at test time. Okay, so if you're able to evaluate, a couple of extra forward passes with transformations of your data, you will get better performance. And in a practical example of this, applied to contrastive learning on downstream tasks appeared in ICLR, or will appear in ICLR later this year. Okay, so I'm going to spend the last couple of minutes just briefly mentioning what I think is next and what I think is exciting. So in the last couple of years, we have made a lot of progress in understanding, especially in the context of deep learning, understanding symmetry, both in terms of what we can do with our neural network architectures and the benefits of using, say, convolutional architectures or feature averaging or data augmentation. But there's still, as I mentioned, some open questions, and this PAC-Bayes bound really, it tells part of the story, but it doesn't. I don't think it really gets to the heart of the matter, especially with the role of equivariance. And beyond that, beyond the theory, I think there are opportunities to operationalize this basic structure in new ways. So this basic structure of equivalence classes induced by a group. We can think of this, say, for maybe a less restrictive set of transformations. So maybe it's not a group, but something more general. I think we can operationalize this in new ways. And there are a lot of connections to pretty old ideas in statistics that sort of had their heyday in a somewhat, I guess, classical setting. And I'm interested in seeing if there are ways we can port some of these new advances or new understandings back into statistics. And then finally, and I think this is what a lot of people are interested in, is learning invariances from data. And everything I talked about so far, sort of we assume some invariances. We know something about the problem where we can assume these invariances. There's a lot of interest in learning invariances where we have a bunch of data, but we don't know necessarily what the invariances might be in that data. Okay, and this type of problem has applications in physics and causal inference. There's a really active literature right now connecting some of these ideas to causal inference. So that's all to say. I think there's a lot of interesting stuff out there, a lot of ongoing work that is quite promising. And in the last minute, I'm just going to tell you about something that I'm really excited about, that I'm collaborating on with some people, sort of scattered all over the world. But this is Jan Dubois, Karen Ulrich, and Chris Madison. Chris is at Toronto, and Jan is currently at Toronto, but will be starting at Stanford in the fall. But the basic idea here is that rather than having a single task Y, say we have image of a cat and we want to label that image as a cat, we might think of a whole suite of tasks downstream that we may not even know what the task is yet. But we might think that there's a whole collection of possible tasks that share the same invariant structure. Okay, so they might have different conditional distributions, but their conditional distributions are all invariant to the action of some set of transformations. Okay, so if that's the case, then there's really no reason to store X in its entirety, at least for the purposes of these downstream tasks. What we'd like to do is just compress it to these maximal invariants. Okay, and so we've done some work, and we have a workshop version of this that will appear at an ICLR workshop, and we're fleshing out some of the details now. hopefully for NeurIPS. But the basic idea is that we can get some lossy compression for lossless prediction. So we don't lose any predictive performance, but we can actually compress the data for use in these invariant downstream tasks, and get a big gain. So I won't go into details of how this is done, but this is basically compressing with a VAE. And if we compare it to a standard VAE, and this is just MNIST, we have the first row is inputs, the second row is reconstructions from a standard VAE compressor, and that allows 99% classification accuracy on a downstream task. And we get, from the standard compressor, there's 130 bits. But if we use our invariant VAE compressor, we get a big reduction in compression, okay, a big reduction in bit rate, and I mean, visually much better reconstructions. This is really only the tip of the iceberg, so we're still finalizing some of the experimental details, but basically we have some really interesting results about using big pre-trained networks like OpenAI's CLIP. And the idea there is, rather than group equivalence classes, these contrastive learning networks are learning some sort of conceptual equivalence class, and we can still compress that, and we're seeing compression rates of reductions or a couple orders of magnitude. So I'm really excited about that, and I'll just say keep an eye out for that. So thanks a lot for listening, and I think we've got some time for questions here.
Okay, can I have a question?
Yeah, Kevin, go ahead.
Yeah, just like from outsider's point of view. So what do you think is really the distinctive benefit of using symmetry properties when there are tons of ways to reduce the size of the model? Simple, like a non-parametric estimation, you start with a simple functional form and then add more complexity. So there are a variety of ways of moving between the larger model to the small model. But then now, I think symmetry seems to be very, very exciting, like a way to think about this problem. But then what do you think is the really distinctive advantage of using these symmetry restrictions?
Yeah. It's a really good question. So I don't think I have a complete answer to this, but typically, if you do sort of reduction by symmetry first, you can still do all of the other things. And actually, there's some classical statistical work on this, I think back in the 60s. But if you can sort of mod out the invariances that you don't care about, and you just retain the necessity, right, the key part, then what's left is a simpler problem. So then you can still do non-parametric estimation, whatever you want, sort of in that reduced problem, and it will be easier. And that's I think, if you can incorporate the symmetry into your model, you basically will always benefit. And I guess depending on what you do with it next, you may benefit in different ways. But typically, the thing you do next will also be simpler, because you'll have reduced the complexity of your problem just by handling the symmetry.
Yeah, thank you.
Yeah. Jesse.
Hi there. So I guess for thinking about data augmentation, is there a generalization or sort of a general way to think about this for people who may not be working with data, just doing function approximation? Is it basically, should I think of this as sampling along any given orbit? Is that the right interpretation?
Yeah, that's a good interpretation. Yeah. So if you could say move along the orbit, apply random transformations to some data point, then you've augmented your data set. That's where the term comes from, right? So you've given yourself some sort of extra observations that they will all share sort of the key part, the important part, and they only differ in the sort of ways you want to be invariant to.
So I guess what I'm a little confused then is, assume that we design our neural network to have the invariance properties we're interested in, then shouldn't it be that if we're sampling along that orbit, shouldn't it, mechanically almost deliver the same result? Or is that actually what we're looking for, is to kind of reinforce that mechanical connection?
Yeah, so if you already have an invariant, so let's say you have a convolutional network with an invariant layer built in, then in theory, there's no benefit from doing augmentation. Yeah, so
Gotcha.
and
Yep.
I think in practice, if you can actually implement the convolution, then you should do that. If you can't, then some of these other techniques come into play. Yeah. See. Michelle? Yep.
Yeah, great. Yeah, great. Very much enjoyed the talk. Yeah. So if you do convolution but without the pooling, as I think is fairly common in many architectures now, then in some sense it's without the pooling. I guess it's not fully invariant, and so yeah. Can you comment at all on that?
I guess I'm not. Is it common to not have an invariant pooling layer?
Or yeah, I'm not an expert on the vision side of things either, but yeah, if my memory serves me correctly, everyone was early on. Everyone was convolving and pooling, and then yeah, more. It seems to me more recently that people have dropped the pooling operator in many instances. But yeah, maybe someone else can comment on that. But they're just wondering if you've given that any thought. But
yeah, that one's new to me, but maybe it shouldn't be new to me. I think if you stick an expressive enough sort of set of layers after the convolutional layers, you should still be okay.
Yeah, right. Okay, fair enough.
But of course, then you don't have an exactly invariant function. I don't know if anyone who doesn't work necessarily strictly on theory has any.
Yeah. No, great. And then I had one other quick question on the. You said the exact augmentation was considered harmful in some way because it might affect the stochastic gradient descent. Yeah. So can you comment? Maybe I just missed that one, the introduction to that, as to what you meant by the exact exact feature.
Yeah. So.
Yeah, exact augmentation. Sorry, was the word.
Yeah. So in practice, this expectation isn't taken exactly right. There's a Monte Carlo approximation of this, right? Instead of applying every transformation, we maybe apply 1 or 2 or 3, right? And so the idea here is that, in fact, it doesn't even need to be exact. This comment about exact augmentation or averaging actually applies to just if you sort of apply too many, if your Monte Carlo approximation, say, has too many transformations applied, it for sure it reduces the variance of your gradients quite a bit, and we see then that the generalization of the trained neural network, it looks like it overfits basically in sort of a classical way.
Okay, interesting. So there's actually a sweet spot in there between kind of between sampling too much and not sampling enough. Okay.
Yeah, that's what it seems like. But I mean, sort of the explanation is still a bit of speculation. That's what we're observing with the experiments, and it makes sense intuitively, but we don't have sort of a good mathematical description of that.
Yeah, great. Thank you.
Yeah, Andy.
Yeah, I was just wondering if there's a reason for the invariance to be described like with orbits instead of just a line or some other equation.
Yeah, well, it all depends on the action of the group. So the cartoons, the name orbit actually comes from group theory, and so the cartoon of, see if I can find, yeah, this cartoon of the orbit just is the cartoon of, it really is just a cartoon. So if it's translation, you know, if the transformation is translation, then you will actually have a line. You know, this won't give you back a closed orbit. It depends entirely on how the group acts on the space.
So they're just showing groups with similar transformational properties, like any transformation.
Yeah.
Okay, perfect.
Yeah.
Thank you.
Can I just ask one more question?
I have time. I don't know.
Oh, okay. Yeah. Just I think in one of the last slides you mentioned about like learning invariance from data for causal inference, and that sounds very like interesting. Can you explain more like kind of activities in the literature regarding this kind of topic?
Yeah. So I mean, it's still. Let's see. There's some old stuff in the statistics literature, and I mean, it really boils down to conditional independence and sufficiency and things like that. And then there's some newer stuff that from the machine learning literature that's trying to make sense of it, sort of coming from a different direction and using much more flexible computational tools. But the basic idea is, at least in some nice cases, you could think of well, let's look at the invariant case. It's easier to think about. You could think of you know, the group action, the set of transformations, as being confounding variables, right? And really, the thing you might think there's a causal relationship between the equivalence class that X is on and the outcome Y. And so what you would like to formulate your model in terms of is the maximal invariant or the equivalence class. And so these same types of ideas are present in some of that literature as well. That's my hand wave. There are quite a few subtleties, but yeah, that's the basic idea.
Thank you. Yeah, thank you.
Okay. Okay, maybe we should stop there. Yeah, but thanks everyone for the great questions and for giving me an hour of your time. And I'm happy to talk offline if anyone's interested in hearing more about this stuff.
Thank you. Great talk.
Thanks, Ben. Let's all give him one last virtual round of applause.
Thanks.
Awesome. Thanks everyone for coming. Yeah, have a good day.